Section 2, Part C, Part 3. Okay, so we've talked about everything to do with the order scheme of things. Back over in the balance scheme of things, we had the mean as the center, and the notion of spread is called the standard deviation. There aren't really any other odds and ends in this scheme of things. So the last major point in Section 2, and it is pretty major, is to discuss how to compute standard deviation. So I didn't write all of this down because it's not terribly important, but I'll just say it aloud. Standard deviation is pretty much what the name implies. It's a standard for how much things deviate. If you want to think of what the standard deviation means in ordinary English, it's the average distance from the center. Now bear in mind, if you're in the balance scheme of things, then your notion of center is the mean, the average. And average is always synonymous with mean. So if you want to make it sound confusing, you could say that the standard deviation is the mean distance from the mean. Well, we talk about all kinds of averages in this course. And here's a second one. X bar, the original thing, the mean of data, is the average of so many numbers. Now we're talking about a second type of average, the average distance from the center. We'll talk about other averages as we go through the course, but it always represents the idea of balance. So what we're talking about here is, on balance, how far are numbers from the center? What is the average distance from the mean? On balance, how much more or less than the mean is your typical number? Take the ovary example that we did earlier, right? The average human being has one ovary. Give or take one. That is 1 minus 1 or 1 plus 1, 0 or 2. So, just a simplistic example. But remember, the average by itself may not necessarily be terribly helpful. So take the other example we were just talking about a second ago in the previous video. If you have a very big peak here and then a whole lot of nothing, followed by a symmetric very big peak over here, then the mean is going to be here, but it's also a very atypical place to be, right? If you've got something bimodal, then the average place to be could be very atypical. If you've got something unimodal, then the average place to be could be very typical. So a lot of it depends on the type of data you have. You need to have a notion of spread to go along with your notion of center. And if the mean is your notion of center, then the standard deviation is your notion of spread. Given that the numbers center, average, balance, whatever, how much more or less than whatever is your typical, your average number in the list? So with this in mind, you would think the sensible thing to do, if you want the average distance from the center, would be to find everybody's distance from the center and average them together, right? Unfortunately, nothing in statistics is quite that simple. First of all, if you subtract the mean from everybody, then some of the numbers are going to, if it's above the mean, you're going to get something positive. And if it's below the mean, you're going to get something negative. And what happens if you add or average either way those numbers together? The pluses and the minuses cancel each other out, and you get 0. Okay, lose the sign, and then average them together. Just talk about somebody's actual positive distance from the mean, and then average those guys together. Well, the thing is, if you've taken anything like pre-calculus or survey of calculus, then you know that absolute value is never your friend in mathematics. Losing the sign is always more trouble than it's worth. In statistical terms, it creates what we call bias issues. This has all got to do with what stuff we'll talk about in section 7, how things approximate other things. And it turns out to be not a very good idea, apart from being incredibly tedious. Another way that you can lose the sign on something is to square it. And this is the typical version of the standard deviation formula that you'll find in most books. I'm just going to say it out loud because we're not going to do it that way. But what most books will tell you to do is you subtract the mean from each number, square what you get, add them up, divide by n minus 1, and take the square root. Now, that turns out to be incredibly tedious for reasons that should be comparatively obvious, right? What, for instance, was the average of these numbers? There were 13 of them, so odds are it's not a nice number. Okay, so if we subtract 18.4285714, and it's still being rounded, from 2, from 4, from 5, then apart from the fact that this guy is still being rounded, it is going to be tedious, right? And that's only 13 numbers. What if you've got 30 or 40 numbers? On the other hand, if you round it a bit more and subtract 18.43, well, that's the worst of both worlds, right? You're rounding quite a bit in the middle of the problem, which is never a good idea. That's how you lose accuracy, and it's still incredibly tedious to subtract from everybody. Likewise, if you call it 18.4, and if you call it 18, it's still going to be on the tedious side, and you're losing a lot of accuracy. So subtracting the mean from every number and then working in 13 columns turns out to be incredibly tedious. And because you probably do have to round before you begin, you end up losing accuracy. There is an alternate version of the standard deviation formula, which in theory results in the same number. I say in theory. The difference is you don't have to do any rounding to speak of most of the time in this formula. And so for that reason, it turns out to be a little more accurate. Mathematically, they are 100% equivalent. But because you don't have to use a rounded number going in, it ends up being a little bit more accurate. I want to be clear on this because this is going to be confusing as we can go on through the course. Just as there are different types of means throughout the course, or averages, there are different types of standard deviations. At the moment, section 2, we are talking about the standard deviation of data, the standard deviation of so many numbers in front of you on the page. That's important. Explicit data. Numbers in front of you. That being the case, we use lowercase s to represent standard deviation. Or if there's going to be two or three sets of data, s sub x, s sub y, etc., if you're going to be unclear on that. Otherwise, we don't generally bother. So lowercase s for standard deviation. Now, when you're computing the standard deviation of so many numbers, section 2 formula, again, there are at least two formulas that are mathematically equivalent and will in theory result in the same answer. The one I'm giving you here is what's called the computational version of the formula. As always happens in this course, the version of the formula that looks easy to use is hard to use, and the version of the formula that looks tedious turns out to be easier to use. So this version of the formula looks a little nastier than other versions of the formula that you'll see. There is a single fraction version of this same formula. Sometimes, if you've seen it in the past, it can be written with the n here, no n here, and the n times this on the bottom. If we multiply top and bottom by n, we can play around with the formula a bit if you've seen a non-double fraction version of this formula. But I think this is probably the easiest way to do it in terms of steps. So it's a little tedious to look at. And again, remember what I said about the sigma notation before. Better to learn it when it's overkill than to be hit with it now when it's something you have to think about. So let me explain how the computational version of the standard deviation formula works. It does not explicitly use the mean, therefore you don't have to worry about whether it's a nice number or not. But the principles are the same. It represents the average distance from the mean. Start by adding the numbers up. If you've computed the mean, you should already have that. Square your answer. Divide by how many there are. N was the number of numbers. Separate to that, square each number and then add them up. Subtract the one from the other, divide by n minus 1, and take the square root. Let me say that again. Add up the numbers, square your answer, divide by n. Separately, square each number and then add them up. Subtract the one from the other, divide by n minus 1, take the square root. Looks tedious, but it's something that a standard scientific calculator can do without too much fuss. It doesn't make you work in 13-odd columns. You can just get on with things. I'll show you what I mean. So we'll do this example in a second, but let's start out with the one we were talking about here. Now we don't need this, and we don't need this, and we don't greatly need the highlighting either. So there we are, and we could make it a little bigger. We could still make it a little bigger. We don't need this guy either. You can probably see that, but I can't because of the game bar. So let's shrink it a bit. There we go. So there's probably 13 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's right, there were 14. Let's make it 13 just so that it's a little more. The uglier the numbers are, the better example it'll be for reference purposes. Nothing's more irritating than doing nice examples in class and then getting nasty examples later. Sometimes it's unavoidable, but let's do what we can. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Whoops. So now there are n equals 13 numbers. And if I add them up, I will get 2 plus 4. I'm just doing it on the calculator here because you're not necessarily going to have Excel handy. 2 plus 4 plus 5 plus 7 plus 8 plus 10 plus 12 plus 16 plus 20 plus 25 plus 28 plus 29 plus 32. Now bear in mind, all that we're doing with the list is adding them up. So there's nothing about the balance scheme of things, mean, standard deviation, that requires you to have them in order. They're just in order from other things we've done. I'm getting 198, but let me double check that quickly on Excel. Yep. So they add up to 198. Now, separately, what I'll do is I'll square each number and then add them up. So the only thing I really have to do with the list is square each number. Now I am going to cheat a bit because I am lazy. There we go. So what we see here is square each number and then add them up. So 2 squared is 4, 4 squared is 16, 5 squared is 25, 7 squared is 49, 8 squared is 64, 10 squared is 100, 144, 256, 400, 625. After that, I'm kind of taking their word for it. 32 squared is 1024. So the sum of the squares is 1024. Oh, and by the way, whoops. By the way, if you get nothing else out of mathematics, notice as we go through this that adding up the numbers and squaring your answer is very much not the same thing as squaring each number and then adding them up. The former will be a lot bigger. However, dividing by n will reverse that. So now where do we stand here? There's 13 of them. They add up to 198. 1024 is what the sum of the squares is. No, that's not the sum of the squares. That is the last square. So let's just cheat a bit again. So 4 plus 16 plus 25 plus 49 plus 64 plus 100 plus plus 1024. Square each number and then add them up, and we get 4332. So where do we stand here? Let me just absorb it. 13, 198, 4332. 4332 minus 198 squared divided by 13. Divide the whole thing by 12. Take the square root. Let's do that again. 13 of them. They add up to 198. The squares add up to 4332. 4332 minus 198 squared divided by 13, whole thing divided by 12, take the square root. So if I start with the 198 and square the sum, then I will get 198 squared, which is 39,204. And then if I divide it by 13 of them, whoops, what happened? It wasn't crazy about that, was it? Divide by 13. Now what am I doing on my TI calculator? I'm just typing in answer divided by 13. And that will not be a particularly nice number, but it's only one ugly number. 30156923 something. And then I will subtract from sum of squares. What am I going to type into my calculator here? 4332 minus answer. Remember, the calculator keeps track of 100 or so decimal places, so I don't lose any accuracy by using that answer button, 307 something. And then I will divide it, the whole thing, by 1 less. Why did it do that again? Oh, I see. It doesn't like that at all. There we go. So what am I going to type into my calculator? I'm going to type in answer divided by 12. Or actually, you can just type, with mine, I can just type in divided by 12 and the answer will fill itself in. And that'll give me 109.69 something. And finally, I'll take the square root. I'm just going to type in square root of answer, and I'm going to get 10.473. I'm going to call it 10.47. Now, because I typed in answer everywhere along the line, I didn't have to do any intermediate rounding. It kept track of it all the way. So it's actually accurate to the edge of my screen here, 10.4734095. That much is accurate, which is a lot more than I need, right? Remember, the more complicated a calculation is, the more you should check it against common sense. What was the average of these numbers? There were 198 of them divided by 13. So the balance point of these numbers is at 15 something. So the question you ask yourself is that a plausible answer? Yeah, I'll buy that these numbers balance at 15. They're in order, but they're not equally spaced correctly, but you get the idea. It is plausible they balance at 15.23. So on average, how much more or less than 15 something is my typical number in this list? What is the average distance from the center? So the question at the end is, will I buy that my typical number in this list, my average number in this list, is 10 something to either side of 15? Yeah, I'll buy that. 15 something minus 10 would put me over in this territory. That seems like a plausible average distance from the center. 10 something plus 15 would put me over in this territory, 25-ish, which again seems like a plausible average distance from the center. Bear in mind, an average distance from the center should be bigger than the smallest one and smaller than the biggest one, right? So given that the average is 15, the closest thing we have is 16. Standard deviation better be more than 1. And the furthest thing away we have is probably the 32. So whatever that is, 17-ish. So it better be less than 17. The average distance from the center should be bigger than the smallest one and smaller than the biggest one. If you add and subtract that standard deviation from the mean, there should be stuff further away and there should be stuff closer in. Now, sometimes the data is very skewed, of course, and it throws you off your intuitions, like if we made the last number 1,000 or something. Remember, everything in the balance scheme is affected by outliers. So if I make the 32 into a 32,000, not only will it make the average bigger, but it'll make the average distance from that new guy bigger. So outliers, of course, are going to pull the average in their direction. And the nature of the beast means that outliers, things that are very far away, are going to increase the average distance from the center. So they're very affected. Mean and standard deviation are very affected by outliers. And as long as we're here, there is a button for this. I'm not trying to teach it, but for my own peace of mind, I would like to double check my calculation. Sure enough. So that's how you compute standard deviation. Bear in mind, the more complicated a calculation is, the more important it is to have a common sense idea of what's a plausible answer. By the way, what is the most common mistake people are going to make here is they're going to forget to take the square root. So if you do that, will I buy that the average distance from the center is 100 something? Will I buy that my typical number in this original list is 100 something to either side of 15? No, that's way too big. So ask yourself if the answer is plausible. Also remember that all of the things we've done, mean, median, min, max, quartiles, IQR, they're all in the same units you had in the first place. Gallons, degrees Fahrenheit, feet, whatever. If you forget to take the square root, then it's going to be in square feet, square gallons, whatever. If you track all the units along, it's kind of hard to do on the screen here. Before you take the square root, it's what's called variance. It's not vitally important to know that, but if you see the term bandied around in the book or the homework, there's occasionally some things that are hard to cut out of the online homework. I am not greatly interested in variance, but you may run across it from time to time. That is to say, standard deviation is the square root of variance. Before you take the square root, it's called variance. After you take the square root, it's called standard deviation. I'm not interested in the term variance for myself. It's not that important at this level, but if you run across it. So let's take another example. Let's take the set of numbers a little smaller. 2, 3, 5, 8, 10, 14, 16. So here they are on the number line presented. 2, 3, 5, 8, 10, 14, 16. Then we can find the average of them. There are 7 of them, presumably. 1, 2, 3, 4, 5, 6, 7. So if we add them up, 2 plus 3 plus 5 plus 8 plus 10 plus 14 plus 16, we get 58. If we take the mean, the average, 58 divided by 7 is 8.2 something. So there we are on the number line where the purple arrow is the mean. That is the balance point. If you had heavy marbles on the number line, all the same weight, then that is where the number line would balance at 8.286 something. I'm sure it's been rounded. But how far is the average distance from the center? The little blue distance marker here. It's a bracket that I've stretched out. The average distance from the center. How much more or less than 8.2 something, 8.38? How much more or less than 8 something is your typical, your average number in this list? Well, square each number and then add them up. 4 plus 9 plus 25 plus 64 plus 100 plus, 256? No, that's 196 plus 256 is 654. So here you see it in all of its glory. There is no rounding that has gone into this. They add up to 58, square it, divide by how many there were, 7, subtract it from what the squares add up to, 654, divide the whole mess by 1 less, and take the square root. Now, some versions of the standard deviation formula that you may or may not have seen in the past have divided by n. There's a couple things to say about that. It is less accurate. This is more accurate. Sometimes books dumb it down a bit at a lower level and have you divide by n rather than n minus 1. But for the long haul, this creates what we call bias issues. Dividing by n minus 1, well, dividing by n instead of dividing by n minus 1 is going to make it a little smaller than it would otherwise be. So that creates some bias issues for the future. We'll talk about them later on in the course. The n minus 1 is the more accurate version of the formula. This has all got to do with degrees of freedom issues that we'll talk about later in the course. The bottom line is, remember I said that all of those signed distances from the center added up to 0. So if you know any 6 of them, you can figure out the last one. That's what we mean by degrees of freedom. We'll talk about these ideas in section 18, way down the line. The bottom line is you should divide by n minus 1 here, not by n. The other thing there is to say about that is I also said that these concepts are much more useful for large sets of data. The average distance from the center of 7 numbers is a curiosity. It's not of any real interest to anyone. For computational purposes, if we're doing this longhand, 7 of them is enough, right? But remember, these concepts are much more meaningful if we have very large sets of numbers. So the other point there is if you've got 1,000 numbers, dividing by 1,000 versus dividing by 999 is not going to make a great difference. But the technically accurate version is the n minus 1 version. So there we go. This is accurate in all of its uncomputed glory. No rounding. The standard deviation is exactly this. And I'm just going to do it on the calculator here. 58, square it, and I get 3364. Maybe I'll write these down. There we go. So if I square the 58, I get 3364. If I then divide it by 7 of them, Answer divided by 7 is 480.57 something. If I then subtract it from 654, 654 minus answer, I'm going to get 173.428 something. And then if I then divide it by one less than how many numbers there were, divided by 6, I get 28.90 something. So that's the variance. And then if I take the square root of it, I'm going to get 5.376. What did I call it here? Exactly that, 5.376. 5.376349 to the edge of the screen. But 5.376 is more than enough. Again, don't worry about how I round things. If they ask for it to 2 places after the decimal, then 5.38, having not done any prior rounding. Take advantage of answer key buttons. If you have to do intermediate rounding, then keep, 5 or 6 places after the decimal until you're done, right? Always keep more accuracy than you think you're going to need at the end. And that will limit the intermediate rounding mistakes. You wouldn't want to call this 481 and 173 and 29. You're losing accuracy at all stages. So when all said and done, will I buy that these marbles balance at 8 something? Yeah, I'll buy that. And will I buy that the average distance of a marble from the purple arrow is 5 something, 5.3 something? Yes, I will buy that. There is stuff further away, and there is stuff closer. Beyond that, you're not going to have a great deal of intuition for it, but as you can see, there should be stuff captured by that distance, and there should be stuff outside that distance. Average distance from the center is smaller than the biggest one. I don't know which side is the bigger one. And bigger than the smallest one, right? So this is 8 and this is 8.2 something, so it's going to be more than 0.2 something, and it's going to be less than whatever distance this is. 8-ish. 7-ish. So yeah, now remember, if you forget to take, let me just go through those steps again. 58 squared gives me 3364. It's not going to let me highlight this. 3364. And then if I divide by 7, oops, I'm going to get 480.57 something. That's this guy. And then if I do 654 minus answer, I'm going to get 173.42 something. That's the numerator. And then if I do answer divided by 6, I'm going to get 28.90 something. 28.9047619. 28.9 something. And that's the radicand. And then if I take the square root of it, I'm going to get 5.376. Again, if you forget to take the square root, the variance is 28.9 something. 28.9 is not a plausible average distance from the center. call it 29. Will I buy that on average a number in this list is 29 more or less than 8? No, it's way too big. So always ask yourself whether the answer is plausible or not, and that will give you a good idea of whether you're right or not. The average distance of a number from the center, 8.3, is about 5.4. A typical number in this list, an average number in this list, is about 5.4 more or less than 8.3. So that's how you compute standard deviation. Now, by the way, lest you think that this is an omen of things to come, I should point out that standard deviation is maybe in the top 3 worst formulas in the course. So this is on the bad side. As far as sheer tedium of calculation, yeah, this is up there. This is top 3. So this is not necessarily ominous in any way. It's just one of the nastier calculations we do in the entire course. I think I will leave off this bit for a wrap-up section. The idea here, if you get nothing else out of what we just did, let's say that these are temperatures. Let's say that these are feet high. Let's say that these are feet high that several bushes and trees are. So if you get nothing else out of what we just did, then if you made all these numbers into inches, well, never mind the rest, it's no longer relevant. So if we multiply every number by 12, if we had heights of bushes in feet versus heights of bushes in inches, then the last thing you would want to do is compute standard deviation again. The others, maybe, but not standard deviation. So that's where we're going next, and we'll wrap it up in part 4 of section 2, one of our longer sections. How to sidestep the process, how to shortcut having to compute all of these things again if you change units. That will take some explaining, and we'll do that in a shortish wrap-up video.